Now this is magnetic dipole. Magnetic dipole. This is all for class 12. So here you see this is a magnet here. A magnet here. This is the north and the south. Here this is your coil. This is your coil which is connected to a battery here. So your current is flowing like this, I current. I current is flowing through here, and let this length be B, and here this length be A, and this is the axis of the coil. So again here you see that the net force is zero. It is this coil is placed in a uniform magnetic field. Your net force is zero. Since your net force is zero, we know that the force at this edge is acting downward, and the force acting here it is upward. It is upward, and this is your axis. So this is A by 2, and this is A by 2. And now here, this force, they are equal and opposite. They are equal and opposite. But since there is a distance between these two forces, so there is a torque. So there is a torque. So here you see in dipole moment, electric dipole moment, your torque was perpendicular to the plane containing Q and E. If the plane is in on the paper, then your torque will act perpendicular upward. It will act perpendicular to the plane, and it will act upward, and that torque will try to rotate the dipole either clockwise or anti-clockwise. That means clockwise or anti-clockwise. Here on electric dipole, it will try to rotate the dipole either clockwise or anti-clockwise. That is making the electric dipole either parallel to the electric field or anti-parallel to the electric field. But in this case, in magnetic dipole, your torque, here you will see, I will tell you in which direction the torque acts, I will tell you. But first of all, because these two forces, it is placed in a uniform magnetic field, your net force is zero, no doubt. But since the force are at some distance, so there is a torque. Torque, it is nothing but it is a moment of a force, which you have learned in class 11. So here your torque will be equal to F A by 2 plus F A by 2. This is the torque. So this is equal to torque, that is going to F A. Now we know that if a current carrying rod, if a current carrying conductor is placed in a magnetic field, if a current carrying conductor is placed in a magnetic field, your force, the force exerted by the magnetic field on the conductor is equal to IL cos B. So here your L is B, so I B cross B. And the angle between B and the magnetic field, this is your B and this is your magnetic field, it is 90 degree. So the direction of, it has been told earlier that the direction of the L will be the direction of the current. It has been told you earlier that, remember these important points. These are the important points which you have to remember. That is the direction of this length, that is the length of the conductor, is the direction of the current. So here the direction of this B is the direction of the current. So direction of the current is upward, and the magnetic field is in the horizontal direction. So the angle between it is B and small b and capital B is 90 degree. So it becomes magnitude of this force, that is, it is equal to IBB. This is your force. So your force here, torque, we are taking only the magnitude. So I have no vector. I have not represented this in vector form. We are considering only the magnitude. So this F is equal to I B into A. So torque will be equal to I B A into B dot B. So BA, this is the area of the coil. So torque is equal to IAB. So this is your torque. Now, what happened here, that this IA, so this IA, so they gave a term to this IA, that is magnetic moment. They gave a term, this IA, this is magnetic moment. Magnetic, you can say magnetic moment. They gave the term this as magnetic moment here. So your torque will be equal to MB. So since torque, it is a vector quantity, B is a vector quantity, and magnetic moment, because it is also a vector quantity, so your torque will be equal to M vector cross B vector. This is your torque. So this is how the magnetic moment, that is, this is the magnetic moment, means magnetic dipole moment. That means magnetic, this is magnetic dipole moment. This is magnetic dipole moment. So here you can see how the magnetic dipole is created. So this is a magnetic dipole. Any current carrying loop, remember that any current carrying loop, it is a magnetic dipole. Any current carrying loop is a magnetic dipole. And from here, because it is a dipole, so there is a dipole moment. So M, it represents the magnetic dipole moment. So see how this magnetic dipole moment is created. Now, since here area vector is always perpendicular to the, this area vector is always perpendicular to the plane. So area vector is always perpendicular to the plane. So the direction of the dipole moment will be in the direction of the area. So the direction of the dipole moment will be in the direction of the area. So here you see that the magnetic field direction, this is the magnetic field. And since the direction of the area is the direction of the magnetic dipole moment, this is the direction of the magnetic dipole moment, and that area is perpendicular to the surface. So it is 2D, which is there, since it is 2D, that means let us take that B is in y-axis, that is j cap, this is B is in j cap, and your dipole moment it is in negative minus k cap, minus k cap, your this is the direction of magnetic dipole, because the direct direction of the area will be the direction of the dipole. So this is minus k cap, that is vertically downward. So your uh, m into minus k into j, that is minus k, that is, this is m, that is, here you see minus k cap cross j cap, minus k cross j cap. So here you see I cap, j cap, k cap. So k j, this is minus I cap, so minus into minus, this will be I cap, that is along the x-axis. So your torque will be along the x-axis. So this is your x-axis, your torque, that is I cap, in the direction of I cap. So again I am telling the direction of the torque. Here you see the torque, because we know that the direction of the dipole moment, that means it is a current carrying loop, and the area of this area, its direction is always perpendicular to the surface. So your area, this area will be in the minus k cap. So this is minus k cap, and here the magnetic field is in j cap. So minus k cap into j cap, this will be I cap. So I cap, that is along the x-axis. So torque will be along the x-axis, and this torque will rotate the coil. Here you see the torque will rotate the coil like this. Here the torque will rotate the coil like this. But in electric dipole, the torque rotate it in this direction. This is the difference between the electric dipole and the magnetic dipole torque. Here your torque will rotate it. Here your torque will rotate it in this direction, but in magnetic dipole, the torque will rotate the coil in this direction along the x-axis, and in electric dipole, it will rotate it in this direction. So this is the difference between the direction of the torque in electric dipole and magnetic dipole. So here you see that is the how your magnetic dipole is created. Here you see how this the magnetic dipole is created, because I can't give the direction of uh, uh, magnetic dipole because it is vertically downward. So in this 2D plane, so I have here written the direction of the magnetic dipole will be in minus k cap, the downward z axis. So here your B is in y axis, so j cap. So this cos it gives I cap. So direction of the torque will be in the in your along your x axis. So I wanted to explain everything in details and make it clear to you all. So this is all about for today.